Good afternoon. This too shall pass. Chem 1A. Okay. It was about chemistry and physics and colors and energy and motion and momentum, all stuff what we talk about here. And they did this whole shot. It was one shot, but it took them 36 hours to really learn it. So the team on the top, the Rube Goldberg team on the top, set it up. 36 hours it took, but it's not cut. It's one shot. Okay. All right. So the last time we have talked about a lot of things, but most importantly, we talked about the behavior of light and that light can behave like it would be matter, like a particle. And we have seen that light has a smallest unit. That smallest unit is a quantum. That's the smallest unit. And we call this unit a photon. That's a photon. That's the smallest unit of light. And as you have the smallest unit of an element is an atom, you can't make it any smaller because then it's not that element anymore. So that's the smallest unit of light. And if you have lots of light of one wavelength, you have lots of photon. You have high intensity. That doesn't tell you anything about the energy of the photon. It just tells you intensity, just that you have much of the same. Okay? Very intense, much of the same. So let's see. I need my clicker here. So I have shown you the photoelectric effect, or I discussed with you the photoelectric effect. And this was to show you that also there is certain matter can take up only certain energy, and this energy needs to be quantized. It is not quite clear in this experiment, but it shows that was the experiment that really got the idea, where the idea came up, where Einstein had the idea and explained it in terms of quantized light. So you have a metal, and that metal has electrons. These electrons are bound, and now you give energy to that metal. You hit it sort of over the head, okay? And give energy to this metal. If you give enough energy to that metal, then it will let go of its electrons and makes an ion. It ionizes, okay? And when you give a lot of the same energy on the metal, it makes more and more and more electrons. The intensity of the electrons is increasing, but the electrons have all the same kinetic energy because you are using, in this case, we use monochromatic light. And if I don't have the right energy or the right wavelengths or frequency, then nothing happens. And this is specific for the specific element or the specific metal. So different metals hold differently onto the electrons. So you need a different kind of energy for different metals to get that electron out of that metal. And once you have that energy, we call this the work function, or the nu zero. That was the frequency, that initial frequency. You have to have the minimum frequency you have to dislodge it. The nu zero, that was this here. This is the initial energy that you need here. For this one, it would be here, and for this one, it would be here. So which one would be the higher energy metal? You would need more energy for this one or more energy for this one to dislodge it? 2. And why is that? Why is that? No, the energy is E equals h times nu, isn't that right? Okay, so the higher the frequency, the more energy you have, that photon, or that light. So if the wavelength is longer, one wavelength is longer than the other, which one has more energy? The shorter or the longer one? Shorter one, excellent, good. So if you now dislodge this electron from the metal, and you have a higher energy than you needed in order to dislodge that electron, that excess energy will be taken up by that electron as kinetic energy. Okay, so let's say I dislodge it with orange light, okay, and there it will have some kind of kinetic energy. If I use now blue light, will it have a higher kinetic energy or lower kinetic energy? A higher kinetic energy, excellent, okay. So and then we have talked about this dualism between the light as a particle, as a photon, and the light as a wavelength. So I've shown you both cases in the last two lectures, and this dualism was then unified by de Broglie. He said, okay, both of them have a momentum. If you have a wavelength, I can calculate a wavelength by having h divided by p, that's quantum. And if I have a particle, I can calculate a momentum, or is h divided by lambda, so that's related to each other. So the last time I asked you a question, and this question pertains, first of all, you need to know that wavelengths and frequency are related to each other, and the speed of light is c. It's a fixed number for us. It's 300 million meters per second, and the speed of light is the product of frequency and wavelength. C equals lambda times nu. Is that correct? Good. So let me open this up for you because you need that here. See, that comes from goofing around here with all this music. But I think that's very enjoyable, at least on a Friday afternoon. Good weekend coming up. Not yet the midterms. That's next week when you have to cram for those. But don't put it off too long, okay? Read the book. You need to read the book in addition to going to lecture, okay? Read the book. I assigned you chapters in the book that you need to read. So we have energy, and energy is never lost. It's always conserved. So if you have a wavelength, and this wavelength would be 400 nanometers, you can calculate the energy. E equals h times nu, and you know that the relationship of the speed of light, you can calculate the frequency, okay? So E equals h times nu, and this is one energy, and so this has obviously, this must have, which one has a higher energy, this one or that one? The 400, okay? So you can split, that's why you can split it in two of lower energy. So you split it in one wave of 1200 nanometers, and then there's another wave coming out, and I want to know from you, what is its wavelength? Is it 200 nanometers, 600 nanometers, or 800 nanometers? You had plenty of time now. Of course, you studied this like there's no tomorrow. You studied this all yesterday, and so I want to know, is it 200 nanometers, that other wave? Is it 600 nanometers or 800 nanometers? One you can immediately exclude. Okay, which one would that be? But that's not the question. Tell me, what is lambda, the wavelength of the unknown second wave? We split that wave into two waves. There's optical devices that do that. The majority has it. That's good. We're not positing it again. So I try to explain it to you. So it would be 200 nanometer. You have this as a fixed energy. Would be 200 nanometer higher energy or lower energy? So that would be great if you have a wavelength with 400 and you split it and you make a higher energy. You can't do that, okay? You would gain energy. That doesn't work that way. So both of them have to have longer wavelengths, right? Now, that means the question was 600 and 800 here. And h times nu is the energy of that one wave. That's, we know, 1200. That's our initial wave. H times nu of the 400. H times nu of the 1200 plus h times nu of the unknown wave, okay? So there's a bunch of constants up in the top. That's why you can forget this. It's 1 over. So if you divide this the wavelengths, what is the wavelengths is nu equals, what is c? Nu equals what? C over what? C over lambda, okay? You put that in here. Here comes C over lambda. Then you have H and C up in the numerator. You can cancel this. So you have 1 over lambda, okay? 1 over 1200 minus 1 over 400. No, 1 over x equals 1 over 400 minus 1 over 1200, okay? So how many times? 3 over 400 minus 1 over 1200. 3 times this. The common denominator is 1200. 3 over 1200 minus 1 over 1200 is 2 over 1200 or 1 over 600. Okay, good. We got that right. So today we're going to apply what we have learned the last time. You need to practice this a little bit. We apply our particle knowledge and our wave knowledge that we have shown with light to electrons. Electrons also behave as, and we know electrons have a mass. Electrons can behave as particles and they behave as waves. And we look at them very often either or, at one or the other. And if we want to explain how electrons position themselves around the nucleus in an atom, we use waves. And this is what we're going to talk about today. So we've seen that here. You see, remember that, just to repeat. The momentum, any momentum of a moving particle or a moving mass, if you run around here, you have a mass and velocity, I can calculate your momentum, okay? I know your weight, your mass, and I can time how long it takes you to go from here to here, so you have a momentum, okay? And this you can calculate the momentum. And you also, a wave is defined by wavelengths. We did this over and over now. And if you square, we come to this later, if you square that wave function here, that's a wave function, you square that, you get rid of these negative lobes here. You flip them up here, and they're all positive, but you have then one here, one here, one here. So it gives you the probability to find something. It could be here, but not here. But I will come to this later. That gives you, squaring the wave function gives you the probability. So, and then de Broglie said, P is the momentum, is H is the Planck's constant divided by the wavelengths, okay? So I can calculate the wavelengths for any particle. I can calculate your wavelengths. Because you have momentum, so I can calculate the wavelengths. I use this here, said, you would have that wavelength. It would be incredible small wavelengths, though, but it would make no sense whatsoever. And with this here, I know, if I have the wavelengths, this is the relation H over P, the momentum is the relation for this. If I have to, I can calculate a momentum from a wavelength, or a frequency. Good, so this is de Broglie's relation. That's the dualism marries the dualism between particle and wave. And now let's talk about certain de Broglie wavelengths. We can calculate this. I have a yellow photon. I don't have to calculate anything. The de Broglie wavelength is 600 nanometer, yellow photon. I have an electron. For an electron, it has mass and velocity. So you need to tell me something about the electron. What's the velocity? So velocity is 100,000 meters per second. So with this, I can calculate now a wavelength. And the de Broglie wavelengths would be 6 nanometers. That's pretty small. A nanometer is how many meters? 10 to the minus 9. So the 6 times 10 to the minus 9. 6 billionths of a meter. So that's very small. Now a sodium atom, all atoms move. And actually movement of atoms can be a measure for temperature. If you have the absolute temperature, absolute zero temperature, it never can be reached because you can't cool down matter that close to absolute zero, because then there would be no movement at all. There's no vibration, nothing. It would be totally still. Doesn't happen because of the electrons. Okay? But you can get very close. Now I can calculate this of a sodium atom at 80 K. This is a relatively low temperature. It's the Kelvin scale. We get to that. It's pretty cold. And it travels at that temperature about 300 meters per second. So if I use that here, I can calculate a wavelength which is 0.06 nanometers. 0.06 nanometers. Now a sodium atom, what kind of radius would it have? How big would it be about? Come on, you know it. How big? Doesn't matter. Any atom. Only nuances. 0.1 nanometer is the radius. Just, okay? 0.1 nanometer. So this is about the size of that atom, isn't it right? That wavelength? This is 0.06, this goes to 0.1 nanometer. And so this shows you that small particles and their de Broglie wavelengths have to be related to each other. If we go, for example, and calculate the wavelengths of a baseball, it's 170 grams, probably they give it in ounces, and I've been told that 40 meters per second is, for an amateur, a pretty good fastball. And so if you calculate the wavelengths of this, you get an incredible small wavelength. 6 times 10 to the minus 26 nanometers. How many meters are this? Come on. 6 times 10 to the minus 35. Multiplies with 10 to the minus 9, you have 6 times 10 to the minus 35, okay? There is nothing that's small. We can't divide anything that's small, okay? It makes no sense. You can calculate the wavelengths of the de Broglie wavelengths of a truck. It's even smaller than that. Truck weighs tons. Doesn't make any sense because this dualism between particle and wave only applies to quantum particles. And atoms and electrons are quantum particles. They follow the dynamics and the quantum mechanical law, right? But a truck is just general physical law, it's general mechanics. So it makes no sense. Now, you know what I probably told you, when you want to visualize something with a microscope, you can't visualize an atom in a microscope. You put it under there, you don't see anything. You see a lot of stuff there, but you can't see the atom. But if you take your hair and you put it under there and you focus it, yeah, you can see the hair. Because the hair is about a micrometer. Something or smaller even. So and the visible light is from 400 to 800 nanometers. That means how many micrometers would that be? 0.8 to 0.4 micrometers. So this is about the same size of that object that you're looking at. So the waves that you bounce off there have to be about the same size, wavelengths than your object itself. Within an order of magnitude, something like this. So if you would, an atom so small, 10 to minus 10 meters, you put this on there, you would have to obliterate it because it can't reflect it back. But you could use electrons. And if you use electrons, electrons are negatively charged. You agree with me? So you could use as your wavelengths, not something that your eye see, but something that you can use in focus because they're negatively charged. You can make a sort of a lens out of it by having a positive, like a funnel that you have positive, so that flies through that funnel. Okay, or the moment it's at the funnel, you switch the charge off, and it flies through the small side of the funnel. And now you bounce it on your atoms, and sure enough, it will reflect it back. It will reflect the electrons and scatter them and reflect them, and then you have some kind of a device to picture that, an imaging device. And with this, you have an electron microscope. Okay, and this is a rudimentary description of how these you can picture atoms, how you can visualize atoms. And now I have a picture here. This has some gold here, and you see the strings of gold here. See that? The strings of gold, and so they are. Or does it go this way? I can't remember. So you can see the strings of gold here, and they're pulling on it, and then suddenly the gold, there's only 2 left here, and then they're all gone. Okay. So, but nowadays this is another picture from 1998. Now we are 13 years later, so I need to get a new picture. Okay. Not that I give the lecture since 1998, but you see here the individual. You don't see it very well, but nowadays we can resolve so well. You can see whole atoms beautifully. So another possibility to use light and the momentum of light, you can stop moving particles. Let's say moving atoms. If you have a sodium atom coming along here. If you have light, this has a certain energy. You know what the energy of a sodium atom is here? Okay, E equals H times 3, and this is the momentum of it, of the sodium atom, 0.06. That's the de Broglie, I'm sorry, not the momentum, it's the de Broglie wavelengths here. So you know the wavelengths of that. Now you have a sodium atom coming along here, and that sodium atom is at 80 K. Let's see. So you know its wavelengths, don't you? Okay, so you have something, a beam of photons coming with the opposite momentum, but the momentum has to be equal. That this negative momentum and the positive momentum should have the same magnitude, the same number, essentially. When they come together, you could actually stop that sodium atom in its track by shining a laser light against it from the other side, by giving it the opposite momentum that it has. So I'm asking you, and this is actually how you get to the low temperatures. So you shine a laser, you cool it down, and then you shine a laser in it, and you stop them in their tracks, and then you use other kinds of cooling. That's how you can cool down. You get to the lowest possible temperature that has been reached was in 2010. It was by a Finnish team, and they reached about 10 to minus 10 degrees, or a quarter of 0.25 times 10 to minus 12 Kelvin. So they came so close to the absolute 0 point, but not totally. Okay. So, but this is one of the first steps to stop atoms, to slow atoms down. You shoot light with opposite momentum at the moving particle, in this case a sodium atom. And actually, somebody won a Nobel Prize for this. His name is Stephen Chu, and he is our Secretary of Energy now. Okay, and he was a professor in Stanford, a professor here also. He used to be our director at the Lawrence Berkeley professor in chemistry here and in physics, and used to be a professor, the director of the Lawrence Berkeley National Lab, the director before the current director. So he won a Nobel Prize for this, and you're doing a quiz. Okay, and your quiz is. Here's the question, I don't have to repeat it. How many of those photons of that wavelength do you need to stop that sodium atom in its tracks? Why don't you give it a stab and think about it? You know, this is the momentum here. P is h of a lambda. You have the lambda for one, and the lambda for the other one. So how many of those do you need in order to stop it? This stuff you need to practice a little bit. You know, I just can sort of put you to the watering hole here with this, but you need to drink by yourself, okay? Or bring in a bar, but you have to pay yourself. Some of you get this right away, and some of you have a very difficult time with this, because it's arithmetic. Did I open it at all? Yeah. I did, okay. Good morning. Pretty good. Pretty good, at least A. No, just kidding. But you're required, though, to have a discussion. So some of you haven't gotten it yet. P is h over lambda, okay? And I have my lambda here, and I have my lambda here. So how many of those do I need in order to stop this sodium atom in its track? Why don't you discuss this with each other, please, and give it another try? You can't forget the h. You don't even have to put the h in there. Okay? It cancels here. Yeah? Yeah? Okay. You don't need the h in there. I'm in red now? Oh, nice. Ah, okay. Yeah, okay. I'm sorry.